What's up, everybody?
Hi, Fook.
Felt like I didn't do enough in yesterday's video, so I'm going to do a little bit more. The word of the day is Munchausen. And the trivia of the day is, what are the notes of a bass guitar's strings in standard tuning? I realized that I should go further into the textbook problems. Oh, now they're not open. Look at that. Oh, no, there they are. So that I do a couple of more difficult ones. And so that's what I'm going to do. I'm going to start off with (46), in case you're wondering. 46. I won't write the identities again. If you need them, you can look at the page in the textbook. Sine to the fourth of theta minus cosine to the fourth of theta equals, and this is going to be sine squared of theta minus cosine squared of theta. That makes sense. Now we start to see why we learned some of the methods of factoring that we did earlier in the year. So looking at the left compared to the right, good rule of thumb is the more complicated expression is the one that you should try working with first. This here is a difference of two squares, because something to the fourth power is a square of something to the second power. So interpreting this as the square of sine squared of theta, then by the difference of two squares, our left side can be rewritten as this. And the right side I leave the same. When I look at this, I recognize that sine squared plus cosine squared, sine squared of theta plus cosine squared of theta is equal to 1. I'll show that. You might be able to just leave off right there, getting rid of it, but I want to show you what I'm talking about. That which was to be demonstrated. It's hard to keep your equal sign in the same place, huh? All right, well, that's pretty good. What looked good that I looked at? $40. Going out of order. $40 for sure. 40 is sine of x plus cosine of x, quantity squared. To the fourth, isn't it? To the fourth equals 1 plus 2 sine of x cosine of x squared. Okay, so I don't know this for sure, but a reasonable guess is that to turn this fourth power into a second power, we're going to square sine of x plus cosine of x. And perhaps sine of x plus cosine of x squared is equal to 1 plus 2 sine of x cosine of x. And then I'll have that one left over squared. So I'll show that just by writing this. Right? It's true that the fourth power could be written as the square of a square. So then I have to square sine of x plus cosine of x. No, I can't distribute the square. We know that. But I could distribute. I could write it twice and distribute, or using the definition of the square of a binomial, a plus b squared. We know that that is a squared plus 2ab plus b squared. So that would be sine squared of x plus 2 sine of x cosine of x. And I knew that in the back of my mind that that could be how I get that, plus cosine squared of x. That's my b squared. And all of that is just the sine of x plus cosine of x squared, so it is still squared. This is a nice time to see that if I recognize an identity, it does not need to be written in exactly the same way. There could be something else in the expression. And especially because of the commutative property, meaning I can change the order of addition, these two things may as well be next to each other, or they could be next to each other. So sine of x plus cosine, sine squared of x plus cosine squared of x is equal to 1. So if I remove them from the expression and replace them with a 1 and change nothing else in the expression, no, that's lazy. Trying to demonstrate good habits. You have to love rewriting something a bunch of times to love this. And again, like I said in the other video, it's a proof. So we're just trying to keep things very clear. So that's good. Where do we get to? 66, I don't know. I think one of these I should really try something where I don't know what to do first, and you should see me try to figure it out. You saw me yesterday in class trying to figure it out. I didn't think that was a bad thing. That's realistic. Didn't take me too long to get on the right track. So number 66, 1 minus cosine of x over sine of x. Plus sine of x over 1 minus sine of x. 1 minus cosine of x. And that's equal to 2 cosecant of x. Well, the first thing I can think to try is to get a common denominator. And so in order to get a common denominator in the first term, I need to multiply by 1 minus cosine of x over 1 minus cosine of x. And in order to get the common denominator in the second term, I need to multiply by sine of x over sine of x. And when I multiply the top, I get 1 minus 2 cosine of x plus, I see, I understand where we're going, plus cosine squared of x. Again, that is a squared plus 2ab, so ab, and multiplied by 2. And that is plus b squared, because b is negative cosine of x. When I multiply, I'm going to get a positive there. Like that. Right? And I'm keeping them separate. Sometimes if you know that you have the common denominator, you could multiply and put them together at the same time, but don't do much more than that as far as combining steps. Now I'm just going to write them in one fraction. Like that. And I'm out of vertical room. Right here, we have cosine squared plus cosine squared of x plus sine squared of x. Out of order, still the same identity. They were separated and we made them into a 1. And so I will write 1 minus 2 cosine of x I see. 1 minus 2 cosine of x plus 1 over 1 minus cosine of x times sine of x. Again, still equal to 2 cosecant of x. Now combining like terms, 2 minus 2 cosine of x over 1 minus cosine of x sine of x equals 2 cosecant of x. And I can factor out a 2. 1 minus cosine of x over 1 minus cosine of x sine of x 2 cosecant of x. Those factors divide to 1. 2 over sine of x equals 2 cosecant of x, which it does. Sure does. All right, great. I don't know, 72 cosine of theta over 1 minus sine of theta? Yep. Cosine of theta over 1 minus sine of theta. Secant of theta plus tangent of theta. Okay, first thing I'm thinking is that I might be able to work with either side. And I think I'm going to try it what I think might be the more complicated way, just to see, maybe you think of this first. When I see half of a difference in two squares, I think about multiplying by the conjugate. Because I think I could get 1 minus sine squared, which is cosine squared of theta, if I multiply by 1 plus sine squared. So I'm going to do that. It's not a common denominator. It's just to get me closer to the identity. And the other benefit is that I see an addition on the right side, and that would be how I get the addition on the left side. Right? So the times where I multiply a fraction or anything by its opposite is when I think that it might be helpful to get the identity, which comes from the Pythagorean identity of 1 minus sine squared or 1 minus cosine squared. So that's one way that I can create that identity. And that's because I can't really work very well with 1 minus sine of theta unless I cancel it out. So then I know that 1 minus sine squared of theta is cosine squared, so I have cosine of theta times 1 plus sine of theta. I haven't distributed because I knew while I was multiplying by this 1 plus sine of theta that this was going to turn into a cosine, which would then cancel with the other cosine of the numerator. So that's why I didn't really distribute. I could have. And that's cosine squared of theta. And like I said, I can see on the left side how I might get to the addition and the separate terms on the right side. I'm going to move up already. like I said, I have one of cosine theta on the top and cosine squared of theta on the bottom. And so one of those factors will cancel. I have 1 plus sine of theta over cosine of theta. Like that. If you don't write the canceling out and you write the next step, I will understand what you did. I would almost prefer that. I find that it muddles your proof to write your simplification on both sides. And so if you're going to do something kind of like what I did here, some people may write that next to the original line, but then it's not even clear what the original equation was. So steps like that of simplifying or canceling out or multiplying by something should be separate and should just also be clear enough in their own step that you can tell that you've done it. So I wouldn't need to see that crossing out. I'm just showing you where that comes from. And we're pretty much there. This, I had given the kind of informal formula. This is true in algebra, period, that A plus B over C is A over C plus B over C. So that's how you can turn one fraction into two separate terms. Which I've said at times is not really the direction we typically go. It is somewhat easier to turn two separate terms or two separate fractions into one with a common denominator. But if this denominator is a monomial and doesn't have an addition in and of itself, then it is possible to use that rule. But there is no rule that we're going to usually apply, which has A plus B or C plus D in the denominator. You're going to apply this when you have one singular term in the denominator. But I can do that here. 1 over cosine of theta plus sine over cosine of theta over cosine of theta. And that's what it is. Pretty good. Maybe 84. Tan of V minus cotan of V, tan squared of V minus cotan squared of V. Tan squared of V, cotan squared of V. Make sure you write these problems down carefully, because if you miss one single sign, you're going to create for yourself an equation which is not true and which will not be able to be verified because it's not true. Sine of V times cosine of V. That's what I'm doing. So the first thing that I notice here is that on the left, well, it's more complicated than the right. It's very unlikely that we're going to easily change the right side into the left. So I'm looking at the left side first and turning it into the right. So I'm thinking about factoring first. That's what I got stuck on yesterday in, I think it was problem 39, is that I was not thinking about factoring before I was thinking about distributing. This denominator is a cotangent. So that's what I mean. Funny I say that. See? Look out. And so I recognize that the numerator is a factor of the denominator, or this here is a difference of two squares. It's also the two trig functions that don't exist in the same trig identity. So aside from turning everything into sines and cosines, which for a little while is going to make things very complicated, I can simplify first by factoring. And so I'm going to factor the denominator, which is a difference of two squares. Why am I going to do that? I know that it's going to cancel. how ironic that as I talked about writing it correctly, I didn't. Not surprised that the more I'm talking, the more mistakes I'll make while I'm writing. All right. These two cancels divide to one, these two factors divide to 1. That's good. Now, putting it in terms of sines and cosines does make sense because that's all I have on the right side. So now I'm going to get a compound fraction with now, I know how a lot of you would do this, and it would be perfectly fine. We would get a common denominator in this denominator, and we would get one single fraction and then use keep, change, flip to get the final answer. But something I did in yesterday's video, and that could apply here, is to think about how I would turn this fraction, compound fraction, into a less compound fraction by multiplication. If I multiply the numerator here and the denominator here by sine of v multiplied by cosine of v, I know that in the denominator, after I distribute, both of these denominators will cancel, which will turn it into a, I don't know if it's proper to say a non-compound fraction, but that's something that I did yesterday and something that you could do to immediately simplify a compound fraction. So in the numerator there, we get sine of v times cosine of v. And in the denominator there, we get, well, when I multiply, I'm distributing. So in this first multiplication, the cosine of v will cancel, and I'll get sine squared of v. And in the second multiplication, the cosine of v, the sine of v will cancel, and I get cosine squared of v. This just kind of gets you there quicker. Does that make sense? I hope so. The denominator there is equal to 1. And we get that. I'm going to cut it there. I think the combination of the two videos that we got now with the answers also that I've posted, please make sure if you're watching this, there are also numerous problems in the slides that I posted for Chapter 8, which just go through in the same process, problems that were either on the homework or are from the same chapter of the homework. It is important to see many methods used to simplify these equations and just get familiar with the tools that you can use. There is no single way that you will verify trig identities. You have to be willing to try things. You have to recognize things that have worked in the past. And the question is never, what should I do, but what can I do? What am I able to do to this expression? What trig identities do I identify in this expression? Can I factor this? Can I make a common denominator? You might not know why you're doing it. Often I don't know what I will accomplish with a particular step, but I just know that I can do it, and after I do it, I look again. And I think, is this closer? Can I do something else that might get me closer? You have to have a much more open mind when you're simplifying these things and just be willing to go in one direction, take a step back, or reevaluate. And then it's fun. It's like a puzzle. All right, everyone, I'm going to walk around and end the video. Have a good weekend.